All right, so this data has every NBA team, their wins and losses for this season, their winning percentage, their records for home, road, division, conference, points per game. That's what PPG is, points per game. Opponents' points per game, so that's like how many they're averaging, allowing the other team to score. And then we have this differential, which is just the points per game minus the opponent's points per game. So this is kind of their average, the average margin of victory, we would say. Average margin of victory. So chapter 4 is about relating two sets of data. Are two sets of data related? So if I asked you, do you think that points per game scored by a team is related to how many wins they have in a season? Do you think they're related? Yeah, I think it makes sense, right? We think they're related. So we want to quantify this relationship. You know, we want to say, well, how strong is this relationship? How close are they related? If you make a graph called a scatter plot, so click Graph, Scatter Plot, and we have to choose which variable is going to be x and which one's going to be y. The x variable we call the explanatory variable, and the y variable is the response. So if they're related, that means that if you kind of knew a team's number of wins or you knew their points per game, then you could probably come up with a prediction for the other one. So if I knew that a team scored a lot of points per game, then that might mean that they win a lot more games, right? So the question is, do we think that points per game explains how many wins they have, or do we think the number of wins explains how many points per game they score? Which one do we think affects the other? Yeah, their points per game is resulting in the wins, right? That's what we should think, okay? So that means the explanatory variable is going to be the points per game. It's explaining the wins, and the wins is the response. It's the result of those points per game. So my x variable, I'm going to choose points per game. And my y is going to be the wins. I think the points per game is affecting the wins. The explanatory variable explains the response, okay? So we compute and we get this scatter plot. Now it doesn't look great, but is there a general trend that you see? So if I were to look at this, I would say, here's the trend, right? The higher the points per game, the higher the number of wins, right? We have this general trend. It's not perfect, but we have this kind of upward movement, okay? This upward movement. That kind of tells us that these things are related the way we think they are. If two variables are related, we say that there is a correlation between them. So correlation means relationship. They are related. If when the x value goes up, the y value goes up, we call that a positive correlation. So this is a positive correlation. Okay? So when the x goes up, the y goes up, we get this kind of left to right upward movement here. Okay, so that's positive correlation. I'll show you another picture. I'm going to change points per game to opponents' points per game. This is kind of their defensive metric, right? It's how many points are they allowing per game. And we've got this trend going this way, right? See that? The higher the points they allow, the lower number of wins they have. So when you have this, as you go left to right on the x values, if the y values go down, then we call this negative correlation. Okay? Negative correlation. Okay. And that should make sense. So we should be thinking about that when we're thinking about two variables. Do I expect there to be positive or negative correlation? I think higher number of wins should mean, or higher number of points per game should equal higher number of wins. Higher means positive correlation, right? It's like two positives is a positive, right?
So yeah, the y value goes up as the x value goes up.
Yeah,
That's
up is positive correlation. Yeah.
And if the y value goes down as the x value goes up,
That's negative.
Okay.
Yes, that's exactly right. So if we're allowing more points, our wins should go down because we're allowing too many points, right? Our defense is not good. So as the points allowed goes up, the wins should go down. Up, down means negative correlation. Okay, so we just think about that when we're looking at that. And when we look at the graph, we need to think, does this make sense? Is it positive or negative correlation? Does it make sense of what the variables are? Okay. All right. So we want to quantify how strong this relationship is. So I'm going to go to stat regression, simple linear. There are these other ones on here, polynomial, multiple linear, logistic. They're all awesome. We will not do any of them. We're only going to use simple linear, okay? We don't have time to do the rest. Sorry. So let's pick the same variables, points per game and wins. Okay, I'm just going to put those in. So I went to stat, regression, simple linear regression. So do you remember the QQ plot? And it compared your data to a normal distribution data, what it should be, and if they were closely related, then we had this line, and if the points were close to the line, it was good. We have the same thing here, okay? So this regression gives us a let's blow this up. So we get all this data that pops out. We'll talk about this in a second. I want you to click this arrow at the bottom. So the arrow will plot that same scatter plot that we just made. So this is the scatter plot. But it's also plotting this line. And this line is called the best fit line, or best fit regression equation. Best fit line, regression equation. And basically it just goes right down the middle of your data, okay? And it's supposed to represent your data. Your data has this trend going up left to right, and this line is splitting right down the middle of that data, okay? We call it the best fit line. It's the line that best fits your data, okay? That's why it's going right down the middle. If you think of it as like an average, it's like an average line, right? The closer these points are to a straight line, to this straight line, the stronger the relationship is between the two. Okay? Why are they not perfectly sitting on the line? Higher points per game should mean higher wins. Unless what? Unless your defense is also bad, right? If you're scoring a lot of points, but you're also allowing a lot of points, not necessarily going to win more games. That makes sense? But in general, scoring more points leads to more wins. Better your offense is, the better. But there's also the defensive part of it too. So that's why these aren't perfectly lined up. Okay? Because there's other things going on, right? There's other things going on. So in this, if we go back to this part, this is going to tell us how closely they're related. So here is R, it's called the correlation coefficient. And that is the correlation stat that we saw in the QQ plot. The closer that guy is to 1, the closer those points are to that straight line. If R is exactly 1, then we have perfect correlation. That means that those points are lined up perfectly on a straight line. Okay? So the correlation coefficient here is 0.748. 0.748. So how do we know that that's good enough? We have a table of critical values, just like we did for the QQ plot. So I know it's in the formula sheet. So this is the formula sheet that you're using on the test, okay? And there's this big table here, and it gives you the critical values for the correlation coefficient. And that correlation coefficient is our R, okay? And by sample size, that correlation coefficient changes. Our sample size is 30. We have the 30 NBA teams. We're treating it like a sample because it's just 1 year, okay? So I'm going to go down to 30, and my critical value is 0.361. So is our correlation coefficient R, is it better than that? Better means it's closer to 1. Closer to 1.
Oh, yeah, yes.
So our, where'd it go? I lost it. There we go. I don't need that one. Our correlation coefficient is 0.748. That is closer to 1 than 0.361. Okay. So let's just summarize what I just said. If two variables are related, then there is a correlation. Between them. If two variables or two data sets are related, then there is a correlation. Okay, so we just say correlation for relationship. We think wins and points per game is related. So we say there's a correlation. Then we have this variable called R. It's the linear correlation coefficient. The linear correlation coefficient. So R is always between -1 and 1. If R is positive, then we have positive correlation. If R is positive, we have positive correlation. If R is negative, we have negative correlation. If R is equal to 1 exactly, then that is perfect positive correlation. And if it's equal to -1, that's perfect negative correlation. The critical value table only has positive R values on it. So if your critical value, or not your critical value, if your R, if your correlation coefficient is negative, then you just take the absolute value of it, make it positive, and then compare. So we don't have two tables that look exactly the same, except one's positive, one's negative, okay? Doesn't really matter. You just, if your correlation coefficient's negative, then take the absolute value, change it to a positive number, and compare it, okay? When you're comparing, so we say if the absolute value of R is greater than the critical value, then a linear correlation exists. So the critical value tells you how close to 1 it has to be, and you compare your R to that. If your R is better, then a linear correlation exists. What's actually happening, we don't teach it this way, but you're actually performing a hypothesis test. You assume that there is no correlation, that the R is 0. and your alternative is that there is a correlation, it's not equal to 0. And if it's far enough away from 0, you say, okay, that's far enough away. We believe that there is a correlation, that it's not 0. Okay? So if R is close to 0, that means no correlation. If it's close to 1 or -1, it's strong correlation. If it just gets past the critical value, you just say yes or no. There is or there isn't. Okay. Well, so let's write that down. R equals, or R close to 0. We'll just say R equals 0 means no correlation. So it's more about, is R far enough away from 0, not is it close enough to 1, but the closer it is to 1, the better. Okay? You want it to be close to 1 or -1. So let's remember this number. So it's 0.748. That was wins and points per game. Okay? So let's change it to opponents' points per game. I'm just going to click Options, Edit, and then change the points per games to opponents' points per game. So if I look at the scatter plot for opponents' points per game, we see we have this negative correlation. So our R value should be negative. So if we go and look at the correlation coefficient, it is negative. All right? That just means, you know, we have this negative correlation. So now the R is about negative 0.51. So the critical value was 0.361, right? So both of these pass the test. If we take the absolute value of this one, it's positive 0.51. That is greater than the critical value. So we still say this is correlated. But which one is better? The first one's better. So that's an indication that in the NBA in this season, that offense was more important than defense. If you watch NBA, you probably agree. But their offensive output is attributing more to the wins than their defensive output. Okay? Now, do we think there's a better one? Is there one that takes into account both offense and defense? Is there a variable that takes both of those into account? Offense and defense. The differential, yes, the difference. This is their points per game minus their points allowed, their opponent's points per game. So let's see what that looks like. So stat, regression, simple linear. Differential is the x, and y is wins, w. Now look at the graph. Now those are a lot closer to the line, right? We see a lot stronger correlation here. And if we look at the correlation coefficient, it's positive, and it's 0.977, which is really high. Like that's really close to 1. This point differential is highly correlated to the winds. If I was going to use one of these three variables to predict how many wins a team will get, I would use the differential. It's taking offense and defense into account. The correlation is a lot higher. So this correlation is 0.977. So that's the winner, okay? Now, why aren't these perfectly on the line? Why isn't it equal to 1? Because, you know, you can win a game by 20 points, and you can win a game by 1 point, and you still just get credit for the one win. Does that make sense? And you could lose a game by 20 points, or just lose by 1, you're still getting 1 loss. So that's why this isn't perfect, because you can have a high point differential because you won one game really bad, and you lost more games by just a little bit, right? You still have a positive differential even though you lost 3 games and only won 1. But in general, though, this gives us a really good picture of this line. If you have your mouse over the line, it'll tell you the equation. You guys remember linear equations? So a linear equation is one you can write like this: mx plus b, right? Where m is the slope, b is the y-intercept, right? The way StatCrunch writes them is it just switches the order here. It writes them as b plus mx, which is fine. You just need to understand that no matter how it's written, the coefficient of x is the slope, and the constant is the y-intercept. It doesn't really matter what order they're in, okay? So this equation is called the least squares regression equation, or the best fit line, okay? So let's write that down. The best fit line is called the least squares regression equation. Or you could say it's the least squares regression line. It's always in this form, mx plus b, or it could be like this, b plus mx. And in our book and in the homework, it distinguishes these equation lines as y hat instead of just y. So we use y hat to say this is the regression equation. This is the regression line. You know, in our data, our y values are the wins, right? So we have these y values in the win column. We're just going to distinguish between this y value. These are y values on the line, okay? Not just, not necessarily in the data. Okay. So this equation is 41 plus, let's round this, 2.709 times x. Times x. I rounded that, so I'll say approximately. So if I were to say, I'll give you the point differential for a team for a season, and you tell me how many wins they had. Okay, so what would you do? If I said, let's say their point differential was 2 for the whole season. They averaged beating their opponent by 2 points per game. That's just their average differential, right? So you would say, well, how many wins would that be? Well, you could use this equation, right? You could say the number of wins should be 41 plus 2.709 times this point differential of 2. And we would predict about 46 wins. I'm sorry? I made it up. I just said, if I told you a team's point differential was 2, then you could tell me a good prediction of the number of wins, right, just by using the equation. On the graph, you can see it here. If I plug in 2 on the x-axis, I go up to the line. The line tells me how many wins, right? 46. That's a terrible line, but I tried. So you predict, you plug in the x value, the equation predicts how many wins you'll get. Okay. Let's look at this point here. What is that? Should be able to click on it and tell me. It doesn't tell me. I have to click on it here. This is actually the first team. This is the Atlanta Hawks. So they had 60 wins, point differential of 5.4. So if I make a prediction for them, I plug in a 5.4 point differential. It's only going to predict about 56 wins, but they got 60. That means they won some close games, right? They won some games that were really close. The line represents the average. This is what, of all the teams that have a point differential of 5.4, we would say their average number of wins would be 55.6. Okay? The Atlanta Hawks got 60 wins. So we would say their number of wins was above average. Okay? So they have a 5.4 differential that predicts only about 56 wins, but they actually got 60 wins. So there's a gap. So the gap between the two, this distance here, between the point and the line, is the error. That's the error in the model. The line goes through the middle, right? The points don't fall exactly on that line. The differences between the points and the line is what we call the error. And we actually have a technical name called residual. but it just means error. It's the difference between what actually happens and what is predicted to happen with the model. So when you go home today, you can tell your friends you did some modeling today, and it was true, right? All right, so this difference is called the residual. So let's write that down. So the residual is y minus y hat.
Is that the word for
Error.
okay.
That's the error, yeah. So you can call this error. It's the difference in the actual y value from the data and the y value that you get from the model where you make the prediction. So we say that this y is the observed value. And this y is the predicted value. And the difference is called the residual. If the residual is positive, that means that the y value is above average. If the residual is negative, that means that point's below the line. That means it's below average. So points above the line are above average. Points below the line are below average. Now, we could say, how do we know that this line is the best fit line? How is it the best fit? Well, we can calculate this residual for all of these points, right? And the line that has the least amount of error is the best fit. Does that make sense? So we don't just add up the residuals because some of them are positive and some of them are negative, right? So the positive and negatives would cancel out. So we actually square these residuals and then add them up. If you take all the residuals and square them and add them up, that's called the sum of the squared residuals. And our best fit line is the one that has the smallest. So that's why this thing has this funny name. That's why it's called the least squares regression line, or least squares regression equation. It's the equation that has the least sum of the squared residual. It's the least squares. Okay, just for short, you say least squares. Okay, you took all the error and you squared them all because some of them are negative, and you add all those up. If you had a bunch of different lines and you did this with, right, this one would be the one that had the smallest amount of error, the smallest sum of those residuals. So that's why it's called least squares. In StatCrunch, it's in a funny place, but right here is that sum of the squared residuals. So you've got SS, that stands for sum of the squared, and then error, sum of the squared error. And it's not very clear that that's what that is, but that guy is the sum of the squared residuals. You also get here the regression equation. Instead of x and y, it actually gives it to you in terms of the variables. So instead of y hat equals 41 plus 2.709x, it says w for wins and differential for x. So it kind of explains what each part goes, right? And I think that is helpful, but it might also be confusing if you're used to just using x and y. But that, it gives it to you there in terms of the variables that you use. Okay, but so you have to know that you picked x for the explanatory and y for the response. Okay. So I want everybody to go back to options and edit. So if you scroll down to this prediction of y, and it gives you x values, I want you to plug in 5.4 there, and then compute. It adds this on at the end, and you see it makes that prediction for you. It just plugs it into that regression equation. So we get 55.6. That's what we got when we plugged this in, right? We predicted how many wins the Atlanta Hawks should get based on their point differential. We got 55.6. StatCrunch will let you plug those in. You can actually do multiple ones there if you use a comma. You can put in multiple x values, and it'll make the prediction for you. Okay, I'm out of time.